Good morning, all. I am Melissa Townsend, the current Honorary Secretary for the Jamaica Institution of Engineers, and I would like to welcome you all to the third segment of our Developers Forum series. The aim of the series is to enhance the knowledge of the attendees of the various standards, policies, codes necessary to design and execute development successfully and appropriately. So just a recap. In the first week, we looked at the basics for the design and constructing foundations, particularly for high-rise buildings. Then in our second week, we were given some guidance on making submissions to the National Water Commission for water, sewage, and subdivision developments. Today, our topic is building design, wind loads, and earthquake loads with speaker engineer Peter Jervis. We will get a guide on the basic design criteria for wind and earthquake loads, particularly for high-rise buildings. Now I will let Council Member Engineer Romaine Smith introduce our speaker for today.
Good morning, everyone. Our presenter today is no stranger to many of us. He is a renowned civil engineer in the field of engineering, a nation builder, a recipient of a national award, the Order of Distinction in the rank of officer class for his contribution in the field of civil engineering and the development of Jamaica's physical infrastructure. He holds a Bachelor of Science degree in civil engineering from the University of the West Indies, St. Augustine campus. He is also a graduate of the University of Toronto University with a master's degree in structural engineering. He is a professional engineer. He's a fellow of the Jamaica Institute of Engineers, a member of the American Society of Civil Engineers. He has also served on various boards and committees in Jamaica. So let me welcome Mr. Peter Jervis.
Am I on? Peter Jervis. Good morning, everyone. As he said before, I hope I'm not a stranger to very many. As the title of the forum suggests, you are a mix of professionals and hopefully developers, because I would like to speak to the developers as well. But if we're outnumbered by engineers, that makes it a little more comfortable for me, because I'm going to make assumptions that we're familiar with applied maths and a little physics as I breeze through quickly, having only been given half an hour or so. The processes for determining wind and seismic loads for buildings in general. We have had a culture and a tradition. I'm going to share a screen now for my own help. Share. And for your reading along with me. We've had a history where we have had a lot of emotional engineering in concerns related to seismic and hurricanes, because we look at the damage and the results of these events, and we ascribe to the damage forces and loads, which may or may not be. Now, it's a global phenomenon. So to the extent that even all across the world, people have been responding and making these determinations in the past on a more emotional basis than technical. The codes have sort of tried to narrow it all down to quantifiable stages and elements with all the considerations that are more focused on the project itself. So let me begin by quickly running through seismic design loads and their determination. As we see here, our island is located along the tectonic fault line close to the northern edge of the Caribbean plate. which runs from Belize over to Antigua and then down to Trinidad and thereof. I don't want to get into the history of events, but you can see by the highlights which sort of by their size represents the magnitude of events around us. And this just points really that this plate is not dormant and we are still live. So there is a fair likelihood that we will have something of the order of Haiti close or onshore in the future. So what that then says is that it is inevitable. Seismic structural design for buildings involves the use of engineering principles and techniques to ensure that a building can withstand seismic events. By withstand, I mean remain standing. Collapse is the ultimate objective of a seismic design, where we have to give room for cosmetic damage and even less important structural element damage. But in all events, at the end of the day, we are looking at staying upright. The design process involves the consideration of the following factors: the building's height, weight, soil type, its location locally, and in a more sort of larger geographic location basis, the intensity and duration of events. Well, one of the primary considerations in seismic structural design is the building's foundation. This must be able to withstand the resulting forces generated by seismic events in order to distribute these forces proportionately throughout the structure. Typically, deep foundations such as piles, caissons, rafts are used for tall buildings, as these can provide greater stability and resistance to lateral and overturning forces. What this really means is that the soil is your host. You're placing the building in the ground, and from the ground comes the ground motion in an earthquake. If the building substantially disconnects from the soil through shear, it no longer performs in its overturning duties. So the business of deep foundations is, one, to get to harder ground, but two, to contain yourself within the ground so that you do not slide along and emerge at the surface and thereby lose your bearing capacities. So that's a quick aside there. Another important consideration is the building's lateral load resisting system. This system is designed to resist and survive the horizontal forces and displacements generated by seismic events and prevent the building from collapsing or suffering major damage. Different types of lateral load resisting systems can be used, including moment resisting frames, which we are all pretty well accustomed to: beams, columns, slabs, shear walls, brace frames, and combinations of these. As you will see, we generally have frames and shear walls in a common combination. But let me not pause there, depending on the specific requirements of the purposes and architectural intent. The use of appropriate building materials and incorporation of features such as base isolation to reduce the effects of ground motion may also be incorporated into design. Okay, seismic loads are based on the result of seismic hazard analysis, which are studies of the seismicity of a region and the potential for earthquakes in that area. The analysis considers factors including historical seismic activity, fault lines, local geology, all to determine the likelihood and severity of potential earthquakes. Moving from that base to calculate the seismic stresses and displacements that a building will experience, we typically use analytical techniques, including static analysis, dynamic analysis, and response spectrum analysis. These techniques allow engineers to model the behavior of a building under seismic motion and thereby determine the stresses and strains that will be generated in the building structure. Overall, the process of determining seismic loads can be complex and detailed, requiring careful consideration of a range of factors. In Jamaica, we have adopted the IBC as a governing code for all design. The IBC really specifies the supporting standards and manuals for seismic load determination and design for all types of buildings. So merely quoting the IBC doesn't really tell you much about seismic codification. It's all embodied in the principle of the following name. The American Society of Civil Engineers, ASCE 7 standard, provides direction and rules on the minimum design loads for buildings and other structures, and the ACI for concrete and the AISC seismic for steel provides the member design and construction detailing and specifications. So it's not all very sort of loosely referred to in the mother document, the IBC, which really presides on every aspect of building design. The C7 also gives design procedures and exceptions for the specific aspects of seismic design detailing that will differentiate between ordinary framework and walls and everything, intermediate and special. These are 3 tiers of detailing and design requirements to qualify a building for a particular type of lateral load resisting system. As I go on, I will explain better on that. The AISC provides a structural connection detailing, which has very important compliance requirements. Steel has nearly been an art for seismic detailing, because every time they thought they had it covered, a little shake would go and reveal weaknesses. So in my view, it continues to be an emerging art, steel detailing. I'll come back on that too. Okay, for Jamaica, we have to look at the nation's ground acceleration characteristics. By our method of design, let me just run ahead so you see what's to come. Right, this is a design spectrum, which we base our whole base share determination around. Okay, so these are our national earthquake accelerations. So here we are in Kingston. Our 0.2 second frequency acceleration as a starting point would be about 0.5 or 50%. Similarly, for the 1 second period, acceleration embodied at that frequency, we are, well, the most of the center of the island is at 0.24. So these are what have been presented to me as the most recent national bases for seismic starting point design. Okay, the values that are picked from the charts are the best estimate of the fundamental ground acceleration in an earthquake for vibration components of 0.2 and 1. These frequencies have been determined to represent the coordinate values for the full spectrum of frequencies in the average earthquake. So these 2 values we extract from this chart, we would help to develop this spectrum. Now this spectrum, let me read what I have prepared. We then build the spectrum below after applying factors for soil type, estimated natural frequency of the building, damping factors, and design load reduction factors based on the lateral load bearing system being considered to determine the static and dynamic base shear factors. So just to really reiterate, earthquakes arrive at a building as ground lateral and vertical accelerations. This is imparted to the building through the ground only. So it is our starting point for determining the effective design earthquake loading on a building. Let me go down some more. The spectrum shows a relationship between the frequencies of ground motion with the forces imparted at these particular frequencies. So let's quickly look. At point 2, we would have put in what we got from the chart at 0.5, let's say, as the acceleration, 0.5 g. And we would have put in what we got from the chart here, 1, at but a lower value than this. This is a generic chart. But those 2 points we get from up here, I call them the coordinates of our spectrum or general building response, the whole spectrum of accelerations at frequencies. You have to understand that an earthquake doesn't come as a pure clean sine wave. It comes as a whole bunched cluster of sine waves frequencies being carried by frequencies from very high resonance level frequencies to very low, tedious, slow ground motion. They're components of all these frequency movements in an earthquake, and they generally are highest within the 0.2 to 0.6 zone, according to this chart. This chart is not really populated for any particular job. So this then gives us that. We then move on. Let us see what I'm saying here. All of this is to demonstrate that earthquake loads are influenced by the location, soil conditions, and the building characteristics and weights. Let me continue a bit because I think I'm not giving you supporting evidence for what I'm saying. Just having a quick look down the road. Okay. There is a context called the soil type, ranging from type A to type F, ranging from solid, very solid rock to solid rock. Type B is the basis for factors of 1 in terms of its influence on this SDS determination. So soil type, our common soil in Kingston is type D, and maybe downtown getting closer to E as you have more fines and clays mixed in. Type F, I would put in Black River, anything floating on peat. So all of those tend to increase. Let's just refer to SDS for the time being. Increases your peak acceleration. D adds about a factor of 1.5 to 1.8 to the starting value. A B would be 1 to 1, no change. And then F would be up by 2.4. So those are the factors you apply to get ultimately your SDS, which takes you directly after incorporating your building natural frequencies. Let me just explain that every building has a frequency. Every building, if you pluck a building, it will bounce back, and that is natural frequency in the simplest of terms. When the earthquake frequencies coincide with the natural frequency of the building, that is generally the value that has the highest force participation. I'm running ahead to mode shapes. Mode shapes are the sort of resonant and otherwise response of buildings. So you have mode shape participation, so that it's not just a single sway that has all the load. You have different types of sway that has components of the imparted earthquake accelerations on the building. One moment, please. Pause. Sorry about that. Just a distraction. So I hope I'll pick up where I should pick up. I think I've sort of introduced you to spectrums and their delivery of seismic responses. This is really very important when we do dynamic analysis. I will show a little more on that after. So building types totally influence the seismic load you consider in your design. Let me just quickly show you some building types. So these are building types for lateral load resistance. A common use is special reinforced concrete shear walls, because this is, if you go to D, all of Jamaican buildings are obliged to be in the design category D, because we're borderline C in the very low instances, but we're pretty well squared in D. So we have to abide by the comments in this column. So we're allowed up to 160 feet high for a special reinforced shear wall building. We're not permitted to have ordinary reinforced concrete shear walls doing the seismic duties. Neither are we detailed plain concrete or ordinary plain concrete. And with intermediate precast shear walls, which one could consider the old Gore homes as being intermediate precast shear walls, you're allowed to 40 feet. Ordinary precast shear walls, not permitted. Special reinforced masonry shear walls. Now, special reinforced masonry really doesn't kick in until we go 8 inches or above for our blockworks, our CMU. And the encasing stiffeners and belts, to use our common descriptions, have to be substantial and detailed according to the highest standard of rebar detailing. Continuing through. So what you will see here is that not many plain masonry, ordinary plain masonry, pre-stressed, not many other building types are countenanced or allowed for D, unless you prove that your equivalent building essentially falls into one of the permitted classes. Because invariably you're going to have hybrids, mixes of building types because of just architectural needs. But the ASC 7 sets down your borders for qualifying for these. And you're rewarded if you're going to build a building according to the permitted, and you adhere to the special or the ordinary or the intermediate as it requires, you're rewarded with a high value for your response modification coefficient. This high value is good because when you get up to the SDS, you're then allowed to divide it by this response modification on the promise that you are going to detail the building according to these rules. If you're not, you're going to have, especially if you look at the non-permitted, you're going to see very low response modification coefficients. Intermediate, you get a little bit there, but anything that is not permitted requires a higher design base share. As we go down, you will see where, well, lightweight, light frame structures with special detailing are permitted because they have no mass. So they're very low mass, so they wouldn't be inducing and creating loads. Here we go now, building frame systems. A steel eccentrically braced frame is permitted because of their ingrained and natural level of ductility. A lot of all of these conditions and rules stem around detailing for ductility, which is the ability of the building to survive many, many reversals of displacement. Ordinary to intermediate to special. Those are just more intense detailing surrounding creating ductility in your beams, columns, shear walls, and all the connections. The connections are very, very strongly protected by these categories of building type. Let me just jump to where a lot of our high-rise buildings tend to get into the dual systems. In reinforced concrete, special reinforced concrete shear walls, ordinary reinforced concrete shear walls, you get very high reduction coefficients because they expect very high performance from special and intermediate detailing. It's a big difference between ordinary and special, and it's compulsory to enjoy using a lesser design load. So the tables are extracts from the ASC 7 that describe some of the lateral load resisting systems and building types. Buildings in Jamaica fall under the seismic design category D, and NP means not permitted. The response modification coefficient is a divisor that has the most influence on the design loads, and the higher values are desirable. Okay, so in essence, the design loads are not a fixed proportion of the building weight and will vary from, thinking of your base shear coefficient, will vary from 0.05 to 0.25, depending on the class of building that you are undertaking. All conventions of referencing to seismic zones 1, 2, 3, 4, and considering Richter values as a guide for design are now replaced by this method of determining design loads that are unique and specific to the projects. Extreme survival. We sort of asked then, how do we treat with a 4 or a 6 or an 8? Extreme survival is determined by the importance factor that we choose to assign to a building. So this ranges from 1, or maybe 0.8 for an agricultural shed, 0.1 to 1.5. This is how we pick whether we can do well in a 6, 7, or higher, as these factors also apply to the costs. So saying that, we choose whether we want to make our apartment more important than it is. To be sure that it survives, it's the last building standing. And we simply increase our design stresses and everything according to the importance factor. So that's how we treat with Richter values and trying to pinpoint what Richter value you want to survive. On average, I think we sort of place everything coming out of a 6 with very little damage, 7 with damage, and I really don't know how to discuss above that. But that's all we can do for you. And these are the code-guided approaches and methods and the basis for determination. All I can say is that if you document your designs to verify and prove that you have abided by the code, your building will do well if built properly, but you will have strong ground to stand on emotional claims of bad engineering when the building shows some major defects after a 7. this is your safety net, to stick to this implicitly and to not break any of the rules required of the building class, building moment resisting system that you have claimed. Chosen is one thing, claiming is seeing it in the ground as specified. Okay, so yes, okay. Now just to show, the load is presented. So seismic load is presented as the base shear coefficient. That is your the outcome of your mode shape and all your other deductions. You have a base shear coefficient, which multiplied by the weight of the building gives you the gross entry base shear, static equivalent base shear. I say static equivalent because dynamic analysis goes beyond just static loads being applied. Let me go and try to explain a little bit about dynamic analysis. Okay, the distribution of lateral equivalent loads to each level is determined by the moment of mass distribution for static analysis, or it's based on mode shape participation in dynamic analysis. Proper dynamic analysis embraces the stiffness deterioration of a building. So you will have it do many cycles of analysis, and with each cycle it reduces the moment of inertia, which is the easiest way to simulate a crack. You reduce the moment of inertia of all the members and do the analysis cycle again, reduce it. So it might do 4 cycles with each with incremental reductions in your moments of inertia to simulate the deterioration of a building during the course of displacements. So that's a good thing about dynamic analysis. It accounts for redistribution of strength in a building as it decays. Remember now, concrete has no tensile value legally. And once it's cracked, there's no gaining back. You put epoxy till it's tired, it's going to crack next door. So there's no claiming back building stiffness once it's all shook up. So you have to come through after even moderate survival, good survival, and perhaps retrofit essential structural points with plating or inserted steel bracing in terms to restore some kind of lateral stiffness integrity. Not full integrity, but stiffness integrity. All right, so the mode shapes, this is just to say that, you know, when we get up to 12 or more floors, we can have even a wiggler like that. This is about the maximum mode that is essential in your analysis, because this has maybe up to 20% of their load distribution participation. This has 50%, your most basic sway. This, which is your first sort of wobble, would be in the 30%, and this is 20 or less. Getting down to here, a single mode shape like that, you won't get that. And they're summed, root mean square summation, to get the average effective load distribution on your building. So that is a summary of how we get earthquake loads. Questions later. Okay, wind design. So we move on to wind. Sorry to jump to such a mundane concern. Jamaica is located in a hurricane belt. The storms have varied impact on the island, varying from full strikes to near passes. and with wind speeds up to 170 mph. These wind speeds are more predictable with the improved meteorological reporting and forecasts, and the effect of terrain has been studied to an extent where the effects on wind can be fully applied in the design process. So I guess in the old days, we just used the wind speed by Bernoulli's equation to find an equivalent pressure. But let me go on. So this is the wind map for Jamaica. This is the most recent one I've got. Don't know if it has evolved further. But it does have 170 pretty well at the western tip and offshore. I would presume it's entirely offshore. And along the shoreline, 165. And the inland flats, 160, and we're getting up into 155 as we get further inland. The North Coast seems to have 170 and then 150 once you get onshore. But you know, you interpolate your values. So most of Kingston would be 150 and 155 or thereabouts for your basic wind speed. The loads from winds are more easily understood as it impacts the superstructure on all sides and in all directions. The design loads have to be derived from factors that will be unique to the project. The building shape, roof shape, height to eave, attached or adjacent buildings, location characteristics, coastal, inland, and the terrain, suburban, urban, bushy. The presence of solar panels, the attachments of sun shading and light screens, and all these new trimmings and accessories that we adorn with. Reentrant areas and cantilevers. To some extent, the natural frequency of the building, and more importantly, windows and walls. Our windows are getting bigger and our walls are getting thinner. So windows and walls are part of the design process. With tall buildings, we have to sometimes consider the wind impact at sidewalk level, tunneling, funneling, concentration of breeze around buildings, and turbulence impacting adjacent buildings. So downwind, you know, anything over 40 miles an hour can generate turbulence 200-300 feet downwind from a building. So anything within that tail can get some buffeting. So in the analysis and design procedure, we begin with the local area wind speed and exposure factors. So Q, which is the basic wind pressure, is derived from its velocity, having to do with the density of air and its velocity, you know, so mass times acceleration is equal to force. So we get Q. This is a pretty standard ratio derived from density and all these other things. The velocity pressure QZ is then derived considering all these little factors. Now, these are the factors I'm going to go on to discuss. Because there again, we can move from a design wind pressure of, let us say, 60. And depending on where on the building it is, it can go down to 10 and it can go up to 180 from that same basic design wind pressure, but it varies from place to place and in your directional considerations. It varies widely. Okay. The speed is taken from the map above. The basic wind pressure is derived from the formula that gives a static uniform pressure as a starting value. The exposure categories differentiate between offshore, coastal, urban, suburban, forestry, flat, bare, as well as distance from the sea. The terrain factors are determined by the proximity to hills, steepness, height, and whether peaks or plateaus. Various shape factors and enclosure classifications also create factors of their own. Overhangs and parapets have their own body of study, and roof pressure distribution is the the fascination that people tend to not recognize. Just to show the determination of factors, if your building is here at the foot of this hill, it's going to have some influence. If it's on the slopes, like all of Red Hills and everywhere around Kingston, there are factors to modify your basic design wind pressure. And of course, you know, if you're on a ridge, you're getting the full compression of the whole body of air up into one little spot. I mentioned roofs. Roofs, depending on the direction of the wind, have drastically amplified forces just because of their shape and wind direction. We've always been sort of, what should I say, tied to a near superstition that the best slope for a roof is 20 or 30. You know, but that works when the wind is in a predictable direction. As when the wind comes upwind longitudinally, all roofs are flat. So either way, you're still facing high pressures, notwithstanding what pitch your roof is, and particularly in the edge zones, 3 and 4, and along the leading edges, it doubles. In some corners, it triples your wind uplift forces. So these factors are very influential on your design, actual design wind pressures. The design loads on a structure can vary from as low as 10 psf to 180 psf on a single building based on all the factors outlined above. The highest loads are generally found at the corner of roofs, with the second highest zones being the eaves of roofs. These uplift pressures are also act on solar panels, which is a new thing and very in the news, that are placed on the roofs. And in situations where they are elevated at levels above 1 meter, the uplift acts on both the roof and the panels. So you have to kind of keep your panels within this sort of narrow, turbulent gap, so that both things are not seen like biplane wings, and each attracting their own uplift. So you really want to either mask the perimeter of panels so that you don't double the uplift on your structure. So that little clearance is pretty important. Roof overhangs and cantilevers are also subject to the highest loads. Actually, they go up to 4 times, 5 times your basic wind pressure, depending on circumstances. Reentrant areas, you know, all 3 sides of the roof contain, you have a static zone there, so it's not so bad. But if you have a little, only 2 sides or 1 side on the back, it gets bad. So all areas of the roof are to be carefully analyzed and designed for wind. That's any roof, even the big flat roof on a tower, where the solar panels will be going. And in determining your solar structures, you have to take into account assorted wind uplift values. Another area that requires specific engineering review and specification are the external windows and doors. The trend towards curtain walls and large panes requires specific wind capacity design and specifications that depend on the dimensions, layers of glazing, and whether impact screens are provided for protection. You can have impact screens that are porous to wind or not so porous. You have to determine the degree of porosity of your wind shuttering for it to really make sense. Because if it is essentially porous or providing just 50% cover, the full wind pressure gets to your window anyway. There's also the negative pressure from inside building. So on the lee, notwithstanding the shutter, if it's porous, the internal or the suction on the lead side will be not much reduced by non-porous shutters. So shutters must be determined whether they're going to help with the wind pressure or just impact. So that's open for discussion. As an aside, it is important to note that multi-story buildings generally have longer spans of beams and slabs, and the columns do shorten and continue to shorten for over 5 years. The long-term deflections of these main framing elements require clearances and compliant mounting for glass panels, or they will begin to shatter over time due to pressure from the framing and mounting members. I have come upon window installers that don't even give you 1/4 inch between the glass and the frame. You know, properly you should have maybe a 12, 16 millimeter rubber rope entirely around your glass panel within the frame, so that it can give and take with the creep and the settlement and all kinds of age creep and concrete maturing, drying out, compressing. Buildings are going to shorten. You can't get away from it. In one of my more recent analyses, the building just shortened by 60, call it 3 inches. And that's, 20 odd floors, not much, but it has shortened. And that shortening is shared among every floor, not just the foundation retreating downward. So that's just one more thing. Let's not break up all the glass because we didn't give the deflection accommodation to it. Okay, that's it for me. Question time.
Okay, thank you for that, Engineer Jarvis. There are a few questions here for you. I don't know if you wanted to show your other part of the presentation.
Oh, well, all right. Yes, just as a sort of a demo of what would I call it, 3D design analysis. Let me find how to share a screen. Oh, I've lost my thing. New share. Share. New share. Oh, share. Yes. Thank you. Okay, just for a quick demo. This is a building that I had sort of done the analysis for recently. It's still a little evolving, but it's a live one. I don't know what you're seeing, but let me go to the input so you can see what it is. So it's this reinforced concrete, all completely framed building that has assorted shear walls here and there. And well, this one is a brute. This is a 2 foot thick, 1 foot thick, I can't remember, 8 inches. We capture all walls and throw them into the mix for our shear wall assembly and disposal. View output, I did a seismic dynamic analysis. So these are just a demonstration of the different mode shapes of displacement, starting with mode shape 1. Let me exaggerate the displacement. Okay. So this is what happens to the building in its first mode of displacement. What I did do, I took some confinement. This is ground level. It's 3 floors below. And I took soil elasticity to help confine the lower underground part of the structure. It does help to reduce, help to fight uplift and all these other things in the floor raft. The second mode, would be more like this, you know, sort of swinging that way. And what you do, you look at this and you see how uneven your sway is, and thicken up shear walls where it's swaying too much, or thinning out where it's not swaying enough, if there's such a thing as not swaying enough. The building also does some torsional distortions, and it's ready in these whole combinations of vibrations and modes, and the accelerations at the different modes. 4 was more vertical. Oops, sorry. Very exaggerated vertical bounce. And 5 was getting into the fancy dancing. So that's just to show, you know, that sort of thing. And to show the role of shear walls, let us reduce this to a realistic deformation, plane stress, maximum stresses. So you'll see that, you know, the stresses in shear walls, they're really working hard. This one shows that it's taking support from the ground. So its peak stresses are where it pops out to the ground in that case. Similarly, this one being a much thinner wall, it wasn't impressed by the ground restraint, but the thicker wall was. So it kind of had a uniform stress until it broke away, and the stress is reduced as you go up. And you can reduce the thickness of your walls as you go up, because they're not working as hard. But you have to watch your maximum rotation and displacements. And those values are sort of hidden in the not in that, in the view output, sorry. In the output file, maximum nodal point displacements. Okay, well, okay. Just to say that the maximum sway of this 11-story up, 3-story down was 165 millimeters. Not as dramatic as the mode shape demonstration is. That was just a quick demo. But the thing about dynamic is that it, as I say, it reduces your building stiffness as it goes around and does again and again and again to allow for cracks. Okay. Ready for the questions.
Great. Thank you for that, Engineer Jarvis. Yes, there are a few questions here for you. Are these wind maps and spectral response maps provided in the current version of the Jamaica Building Code? And if so, how does one get a hold of the code?
Okay. These were presented for consideration for sending to the ICC to help with their build out of our IBC code. The ICC is developing a build out, a Jamaican ICC, IBC, another language here, IJC. So it was in the code committees under consideration for updating that. It would be in an application document for our earliest very cumbersome assembly of code tie-ins to the IBC of the 2003. But we're going to now combine it all into proper IBC code. So this is an extract from code committee information. But I've circulated it, so you can get it. It's very same base document. It's there. No harm in using it.
Okay, thank you for that response. And just for note, the building codes can be accessed from Bureau of Standards Jamaica, so you can just easily call them or email them to purchase those codes. Another question here, considering restrictions that may exist in the Jamaican building environment, such as limited land space in hilly mountainous areas or high water table in coastal areas, what new technology would you like to see developers and designers take into consideration for seismic readiness of current and future building construction?
Okay, principally be accepting of lighter buildings. We really should be using we shouldn't be using buildings that are massive or too heavy, because it is by the own weight of the building that you have seismic stress. So try to move to more use of very light flooring systems, you know, composite deck. And all partitions ought to be lightweight. You know, bulking up a building with tons and tons, you know, 30, 40 tons per floor of partition CMU walls is not helpful. Hillsides are not a problem, provided you can fit your foundations properly into the hillsides. Luckily, most of our hills, apart from Garden Town, but most of our hills are limestone and very accommodating of any kind of structural impositions. Shoreline, there's nothing. What happens in saturated soil is that your peak bearing stresses at the tips of your shear walls can deform your rafts, and you may not get soil support rebound, and you may not get soil containment for uplift of your shear wall footings in particular. Bending in columns is not a very big set of stresses, but your shear walls are trying to punch into the ground or lift it out. You know, it's something that is being prized along. So the confinement of that can be compromised by wet soil and too much clay. So what you do is at the tips of your raft, you put some piles to cope with the super seismic loads. There's nothing systematically available more than so to make anything any easier. All I say is the lighter the building, the better.
Okay, we have another one for you. This person saying, good morning, Mr. Jarvis. Does increasing the height of parapet walls at roof elevation diminish suction pressure stresses?
Yes, it protects your, if you can get 2 feet above your solar panels, they won't be feeling much of a pinch. It does a lot of screening of your edge concentrated and corner concentrated uplift forces. So feel free to parapet up the place.
Okay, thanks for that. How do you model the soil lateral support in the basement?
Okay, you start with its at full depth rated elasticity, and you linearly reduce it to 0 at the surface. So you vary your spring rates at the floor levels as you go up, reducing as you go to the top. But it's all just like how you would model a raft with springs. You know, you have so much force as it compresses, and that is really okay. You do it on the side, starting with the base value at the bottom, and you reduce it to nothing, because at the top, the wall will push away the soil, because there's no vertical overburden to keep it against the wall. I mean, we're dealing with 10 millimeters or so, you know, we're not getting that much of a well, it depends on the size of your basement, that too. So it's just a straight linear interpolation. If you look at pole foundation design, it really has a bubble at the top, but because it's seismic, you ignore that, because the dynamics kills the surface rebound capacity to sustain any good confinement. So it's lower down. So you start at 0 and increase down to the bottom.
Okay, that's clear. We have a question here from one of our past presidents. While the topic is focused on the design aspect of dynamic loads, would Engineer Jarvis be able to speak briefly to any complementary points of interest related to engineering supervision during the implementation of such design parameters vis-a-vis critical quality control and quality assurance, design adjustments, those kind of considerations?
Okay. We have a obligation to stick to the rules of design and the detailing in particular, if we have chosen a particular type of building. It is to our, what shall I call it, discretion, how well we do that. But somewhere in the building code is a requirement for peer reviews for anything above 5 or 6 floors. There ought to be a signed off peer review for any design, and that will capture omissions of any importance in a design. The detailing should be reviewed also, because how well you impart in your drawings and details the important stirrup encasement of column beam joints, splice locations, stirrups in the columns in particular. The column must survive. So all design should be strong column, weak everything else. So it's a struggle with architects. I don't want to give you any more column space, and I don't want a column there. But you can do without the column and do without the building as well later on. So we have to fight hard to get our columns and shear walls in abundance. And we have to detail, and our contractors are reluctant to do the hard things. It's not tons of steel, it's not a lot of whole lot of reinforcement. It is more confinement reinforcement. Stirrups is the password for reinforced concrete and survival. And that's an on-site management as well, because they tend to like to box up and drop in the cage before you see it, and then they say they leave out this, and you have to start putting in half stirrups and so on. You have to be prepared to work with remedial steps sometimes to keep the work going. But it's a through and through thing. Basically, the business of us designing a building and not being able to decide because it's a separate contract that is tendered and won by somebody else is folly. It's so silly. You don't have a linear thread between engineer of record and the build structure. So quality control should remain with the designer, in a few words.
Yes, thank you for that. A few more for you. Are these analyses being applied to residential buildings in Jamaica, or are they mainly focused on commercial high-rise buildings?
Well, let us say that they are applied to high-rise residential buildings. By residential, if we mean 2-story homes, townhouses, they are intrinsically strong. Almost every wall, because of the mass and the height of these buildings, every wall is performing as a shear wall, even though it may not be lit. There is a small building code which essentially bypasses these strictures as described in the big master code. So the small building code will tell you what you have to do to stay in the boundaries. Our new, and not new anymore, but for the last 20 years, we've moved from CMU, small scheme homes, to port wall. Port wall is intrinsically wonderful. That is, a mutual set of perfectly skinny but functional shear walls. So custom homes, 3,000-4,000 square feet, generally have so many walls and are such that collapse is not a concern. Certainly cosmetic damage by our method of building with rough casted and rendered CMU walls rigidly fixed to each other are going to crack look like hell. But I don't see that we're running on the brink of collapse in our residential homes generally. And the high-rise residential ought to have been designed according to these things. I mean, this has been around, this whole approach has been around for at least 15 years. So, you know, it should be, look, what's very important is that it should form part of your undergrad education. You cannot design anything but for seismic and hurricane in Jamaica. So why graduate unable to do so? And then you have to go back and do a master's or a special course or seminars to learn it. It should be part of the basic lineup. It shouldn't be something special, rocket science. It's not really that intimidating. It's just a little tedious. And we have software that punches it out.
Okay, thank you for that. So basically it starts from the beginning, from school, to make sure that everyone utilizes the code.
I would like to. It's, you know, I'm not forcing you to, but I would like to.
Yes. Another question for you. At our last, well, JIE's last Developers Forum, it was mentioned, well, numerous types of centers being deployed and permanently installed in innovative foundation designs in South Florida. What has been your experience with that type of technology locally?
I'm sorry, I missed the description of that. What happens in South Florida?
They actually employ sensors into the foundation designs to track if there's anything out of balance or out of place or out of the design criteria. So there's an alarm, well, that would alarm in case there's any change. So do we actually do that in Jamaica? This person is asking.
Oh no, we do not do that. That is you know, that is more a sort of that probably started out as a statistical gathering exercise to no, I'm not seeing the value of that. I can't really grasp the value of it because we can only do preemptive quality control, post discovery. It may have value for the 40-year check, which is what's happening to all tall buildings in Florida. They're going through a 40-year age check because of north side, south side, seaside collapse. I'm just sharing a screen of how, well, let us just say, how easy it is to go through the whole seismic base shear determination. There is software that accounts for inputting your local accelerations, applying factors for the soil, applying your all factors, and you come down at the bottom somewhere in there. It's 0.08. You know, it's not difficult. It can be done for every little thing you do. And even if you did it manually, it's not that bad. Wind load, again, you can load up your building and get all your little wind pressures everywhere, you know. And you apply that to your model and off you go. Or you simply do manual, do the maths.
Okay, I think we have I see 3 more for you.
It's an old Bible here, the old Bible. We're at 22 now, 722. But this is the guidebook that we start with for loads. It even gives you floor loads, you know, covers everything. Rain loads, snow loads, every load. Sorry, carry on.
Oh, no problem. I'm happy that you shared the codes that should be adhered to. This person is asking, to what extent does the architectural geometry aid in earthquake resistance design?
Oh, you need a cooperative architect because we tend to put bulges in their walls. We tend to steal saleable square footage by thickening up our walls. We tend to have columns in the middle of the living room, all of which they don't like. But not every apartment building is a single-story bungalow. And if you're going to go up, you have to give room to our needs. We should rule and have full authority on shear walls and columns. Our current trend to fit 3 parking bays between columns is forcing our grid spacing out to 30 feet almost. The increase in cost to span anything from 20 out to 30 is related to the square of the span. So it more than doubles your cost to take a beam from a 20 to a 30-foot span. A lot of these things, well, developed because it was the optimal way. So our old government and school buildings, everything was at 14 and 18-foot columns everywhere because it was the cheapest. As your spans go up, your costs go up by the square of it. So, architects have to be argued with to keep things viable. And generally, car park spacing grids just don't help with apartment spacing grids or hotel spacing grids. So basement parking can be a real pain. And that is where the struggle is nowadays. We have to be parking in basement for everything.
Yes.
Next.
Yes, we have. How do you ensure that your seismic mass is transferred to your shear walls?
Through the foundations. Through the foundations. If your foundation slip and slide and cut its groove because it's not big enough and it's just not deep enough, your footing will rattle around in the dirt and no movement will be passed to the building in an organized way or at that point. And most of it will enter from another point, which develops eccentricities because your ground motion isn't arriving uniformly to the building. Now we balance the response by thinning out or thickening shear walls till they're pretty well uniformly balanced. And then we go and look at the footing to see that it has enough depth, embedment, and cohesion or piles to anchor it, to receive that ground motion coming in. So we don't want the footings to be shallow for any kind of multi-story building. Fortunately, basements put us right down in the ground. So there's no slipping and sliding there. So there's an intrinsic good in basements. But it's never really a primary concern.
Okay, I think that's noted. What is the consideration for the use of CMU wall interaction with the concrete beam and column frame?
Legally, it doesn't apply to our D type seismic classification buildings. But it works. So if you had all pockets filled and you had horizontal mats, I much prefer the ladder mat, but horizontal, a pair of horizontal bars every 2 rows, you can demonstrate that there is enough shear strength in your wall to match an equivalent RC wall. So there is some, what should I call, damping effect and some amount of usefulness in CMU walls, but it's going to give up when you get past the 6, the 6 in the Richter scale. So it's not good to, we're not allowed to consider it as an active part. This is multi-story now, not houses. Houses don't have that level of displacement and mass to contend with. So it's not legally a shear wall, unless it's a bigger block than usual and all pockets and everything reinforced and bells and stiffeners.
Okay, thank you for that. We have a raised hand here from Past President Howard Chin. Engineer Chin, you may go ahead with your question.
Yes, with regards to rebar, I noticed that the general thing is that they use vertical rebar, but in shear walls. But why not put rebar diagonally rather than vertical? If you want to,
I quite agree. I think it's just counterintuitive to the normal intuition, but definitely diagonal mats would perform far better for a dedicated shear wall. It's just a buildability problem. I mean, what I have done is put diagonal column profiles, rebar cages within shear walls to really give it that extra, shear capacity. But that's what we can do. We can do supplemental X-bracing within the concrete wall.
well, if you're using a cast wall, can't you then put in diagonal?
There is it's a route to, one of a route to, let us call it better engagement of the rebar. But I think the constructability problem is not worth codifying it.
All right, thank you.
Actually, the essential strength in the shear walls are the column cages at each end, which are called the end zone, the confined end zones. That's where everything really happens. The middle of a wall really, it's really just there to keep the two ends far apart, because it is a vertical beam, and even in shear, the concrete is doing most of the shear transfer, but it is the compressive and tensile edge forces that are the real thing to look out for.
Okay, thank you, Engineer Chin, for that question. I think we just have time for just two more questions. So the last two questions are, well, how do you differentiate between special moment frame building system, intermediate, and normal?
Oh, but let me just start with splice lengths are much higher. The stirrup spacings for everything is, just think, quarter the dimension is the maximum stirrup spacing basically for special, and it goes to half in intermediate. And ordinary is, whatever you learn in undergraduate. So in Jamaica, we shouldn't be using anything but intermediate and special. And it's a lot of specific detailing and control of anchorage. Columns must not host pull-out forces from beams, because you're going to destroy them. So you have to have your beams, in the most extreme cases, protrude on the other side for anchorage and not within the core of the column. The whole objective is to not destroy your columns. So you will find that in steel frame structures, ideally there are no more holes in the flanges or the web of the columns, because that's where failure starts. So what we now have are splice plates, connector plates springing out from the web, up over on the plates for bolting beams to the columns. The whole detailing has changed. So that differentiates between special and ordinary. The ability to survive extreme ductility stress. It's all set out nicely in the ASCE 7 and the ACI code, chapter 19, somewhere around about there, 21. And in the AISC steel seismic detailing supplement.
Okay, thank you for that. Last question. What advice would you give to graduates seeking to practice civil structural engineering in the context of developing one's knowledge and skill in same?
Okay, particularly in the context of today, structural, it would be to familiarize yourself with the codes. To that I mean, know what page to go to find what. Breeze through them, and you will realize that every consideration has been addressed. You know, what I ran into was a special seismic detail now for a freestanding wall. I've been kind of waffling through life. Luckily, my waffles were on spot, but nevertheless, everything is provided for in the codes, and I mean, they refer you off to specialist supplements that you may not have to go and find. But a tedious walkthrough, the ASCE 7 in particular, will give you, open your eye to all the considerations of design. It's just a personal familiarization, a curiosity, a keenness. Nothing better than supervised practice to have, you know, an elder oversee your work and comment on it and score it to some extent. That helps. But you have to have an ease with physics and just to feel things, to be able to visualize deflections as it relates to forces and reactions and responses, understanding, being at home with these things.
Okay, thank you for that. And I guess I should ask if you're hiring any young engineers, some may want to get that knowledge straight from you, Engineer Jarvis.
Well, yeah, but we're always happy to seminar. So if we call sometimes, but also for their party management. But papers and little preparations that they can have to put their eyes to the state of affairs for seismic economy.
I'm not sure if we've heard you. Can you repeat that? Can you repeat that, Mr. Jarvis? It sounded like a choppy a minute ago.
So,
Oh, it looks like since we're nearing to the end, the audio is getting a little choppy. We can see you, not really hearing you correctly. hearing you actually, but we're actually at the close of our session. And just for everyone, the recording of this will be on JIE's YouTube channel. I'll allow our graduate engineer, Janelle Crawford, to just close for us.
All right, thank you, Melissa. Good morning, everyone. Mr. Jarvis, thank you so much for your presentation. It was very fruitful, very knowledgeable, so much information on seismic and wind loads for the design of buildings in Jamaica. You spoke to the seismic structural design for buildings, and you said that it involved the use of engineering principles and techniques to ensure that the buildings are able to withstand seismic events and the design process includes various factors such as the building's height, weight, soil type, location, intensity, and duration of events. One of the main considerations for the seismic structural design in buildings is foundation. Another important consideration in the designs is a lateral load resisting system and the use of appropriate building materials, as well as the incorporation of various features, including the base isolation to reduce the effects of ground motion, is also important for the design. You spoke to the importance of using the various codes, and the one that's used and adopted in Jamaica is the International Building Code, and that includes the American Society of Civil Engineers, the ASCE 7 manual standard, as well as the ACI 318 codes for concrete and the AISC seismic provisions for steel. You said that in the analysis and design procedure, we must begin with the local area ground acceleration, and all of that was for the seismic load designs. And for wind designs, you spoke to various things such as the ease in which it is to understand impact of wind loads on the superstructure, because it affects all sides of the structure in all directions. So once again, I want to thank you for your presentation. It was breathtaking and there was a lot to learn from it. And I also want to thank everyone who joined the discussion and joined the presentation this morning. Thank you all for sticking with us throughout the entire session. And I just want to remind you that JIE aims to promote the practice and the science of engineering, and it's done through various things such as the Developers Forum series, which is what we have going on for the next few weeks. And the last session is going to be on March 30th. The title of this session is Implications of the Development Orders on the New Kingston and St. Andrew Landscape. Thank you all for coming and have a good morning.
Sure. Very nice. Thank you.
You're welcome.